With our sum and difference formulas for sine and cosine today. So we've combined these two together, sine and cosine. Here's kind of the bottom line. The cosine of A minus B is not the cosine of A minus the cosine of B, just as the sine of A plus B is not the same thing as the sine of A plus the sine of B. Long version here is we have some formulas down here, which I'll talk about in just a second, but the proofs of these are going to be left for work in calculus. Right now, we simply need to know these identities. So the cosine of A plus B is the cosine of A plus or times the cosine of B minus the sine of A times the sine of B. In other words, if we have two different angles, such as, we'll say 15 and 20, we rewrite that to find, or in our formula, the cosine of 15 times the cosine of 20 minus the sine of 15 times the sine of 20. That's what we're talking about here with two different angles, A and B. In this case, I have numerical values in there. We expand those out into this difference formula for sine, or for cosine. Cosine of A minus B, cosine A, cosine B, plus sine A, sine A, sine B. What I would note here is, at least in my mind, the operations are opposite of what you'd expect. Notice we have a sum here, but we're subtracting our two products. We have a difference here, a difference of cosine, but we're adding the two products. So same pattern, different operations in between. Then we have the same idea down here for sine of A plus B, or two different angles. Sine of two angles added together, sine of A cosine B plus cosine A sine B, and sine A minus B, sine A cosine B minus cosine A sine B. You can see those have a different pattern, but kind of the shortcut version here is, by the time that you've worked through today's, I think these patterns are simple enough that you'll know these and won't have a lot of issues as far as knowing what these are. Little side note here is I will give you these identities for a particular test, even though, again, I don't think you'll need those. But along with these four identities, we'll also need to know the values off of our unit circle. Well, it might not be a bad idea for you to go ahead and get that out right now, because we will use that quite a bit here for our identities for sine and cosine, and also our next couple of days for tangent moving forward. So unit circle does come back into play here. Hopefully you have that handy. So we'll jump right into some examples that are going to illustrate our sum and difference formulas. You can see the first one here says find the exact value of each function. Should probably say using sum or difference formulas. But with that being said, in conjunction with our unit circle, there are two angles, or more than two possible sets of angles, I guess, but in the first quadrant, there's two obvious angles that we can add or subtract to get 15 degrees, and we could take 45 minus 30 to get 15 degrees. Now, obviously, you could go around your circle. We could do 60 minus 45. We could do 135 minus 120. We could do 150 minus 135, and so forth. Just makes more sense probably to work in the first quadrant. But now that we've chose to use 45 and 30, notice that's the same thing as 15, so we just replace 15 with 45 minus 30. Again, two angles that are on the unit circle. We'll go ahead and expand that out into our version that we just talked about up here. Oops. Our cosine A, cosine B, plus sine A, sine B. So we have the cosine of 45 times the cosine of 30 plus the sine of 45 times the sine of 30. Now we are working off our unit circle, so we chose two angles that were on our unit circle. That way we could find those values fairly simply and make our substitutions. And it does say an exact value, so we're not using the calculator. If you go to the unit circle, on the unit circle, the cosine is the x value. The cosine of 45, you should be able to locate to be the square root of 2 over 2. If we go to 30 degrees, again, cosine is the x value. At 30 degrees, the cosine is square root of 3 over 2. Going back to our 45, the sine is the y-coordinate. That is also square root of 2 over 2. And the sine of 30, again, the y-coordinate of 30 degrees is 1/2. So we've made those substitutions for our functional values. And now we'll just simplify here. If we multiply square root of 2 times the square root of 3, get the square root of 6 over 4. 2 times 2 is 4. Plus square root of 2 times 1 is square root of 2 over 4. And we could write this as one fraction. It's be the square root of 6 plus the square root of 2, excuse me, all over 4. So there is our exact answer for the cosine of 15 degrees. I'm going to hope or assume we all remember our operations for radicals from Algebra 2, but the square root of 6 plus the square root of 2 can't be added to be the square root of 8. They're two separate values, just like adding an x and a y. And these values are underneath the radical, so they can't all be divided by 2 because this answer, this number is not under a radical. Okay, so cosine of 15 degrees, an exact answer is square root of 2 plus the square root of 6 all over 4. We'll start all over again here with the cosine of 5 pi over 12. Since most of us probably don't like to work with fractions too much, I would suggest we pull the 5 pi over 12 off to the side and convert it to a degree measure, so it's easier to find two numbers we can add together to get add or subtract to get, in this case, 5 pi over 12, or whatever the degree measure is. So I go to simplify here. The pi's will cancel. The 12 and the 180 will be a 1 and a 15, and 5 times 15 is 75 degrees. So what we're finding here is the cosine of 75 degrees. Now it should be pretty easy to pick out two angles we can add or subtract from our unit circle. So in this case, we'll do the same thing. We'll do 45 and we'll add 30. So 45 plus 30 does add to be 75. And we can go ahead and expand out into our sum formula, which I'll point out is up here. Cosine A, cosine B minus sine A, sine B. So the cosine of 45 times the cosine of 30 minus the sine of 45 times the sine of 30. So you probably notice very quickly here that we have the exact same setup as here, except we have opposite operations. So we could probably shortcut this a little bit, but I'm going to go ahead and write out the terms as we did last time. The cosine of 45 is square root of 2 over 2. The cosine of 30 is square root of 3 over 2. The sine of 45 is square root of 2 over 2. And the sine of 30 is 1/2. Going to go straight to our simplified version, or single fraction this time. Square root of 6 plus, or minus, sorry, square root of 6 minus the square root of 2 all over 4 is our cosine of 75 degrees, or the cosine of 5 pi over 12. So there's a note to make, is you'll find as we go through here, a lot of our answers are going to look like this. Square root of 6 minus the square root of 2, square root of 2 plus the square root of 6, and so forth, all over 4, because we're using those same values off of the unit circle. Oh, we'll go ahead and move on here. The sine of 105, two angles that we could add or subtract from our unit circle to get 105. I would probably add 60 and 45. Again, there's other combinations to work with. We could do 150 minus 45 if we wanted to. But for my money's worth, it's easier to work in the first quadrant most of the time. So we're going to go with sine of 60 plus 45. So expand that out. We have the sine of 60 times the cosine of 45 plus the cosine of 60 times the sine of 45. Don't know if I can squeeze them on the same screen at the same time, but I can. So notice I put the sum formula right here. Sine A cosine B, sine A cosine B, plus cosine A sine B, cosine A sine B. So our A and our B are the 60 and the 45. But once we have that expanded out, we're going to go ahead and put in our functional values from unit circle. So remembering sine is the y-coordinate, so find 60 degrees on your unit circle. The sine of 60 is square root of 3 over 2. Cosine is the x-coordinate of 45. The cosine is square root of 2 over 2. The cosine of 60 is 1/2. And the sine of 45 is the square root of 2 over 2. Square root of 6 over 4 plus the square root of 2 over 4. So you can see, as I mentioned already, we have that same type of answer again. Square root of 6 plus the square root of 2 all over 4 for our exact value of the sine of 105 degrees. Okay, so there's our look to begin with here. Have a couple more. Number 4, notice we're already expanded out. We have cosine times cosine, sine times sine. I know we've just introduced the sum and difference for sine and cosine, but hopefully that pops out and rings a bell to us. So I'm going to scroll back up just a little bit to look at our formulas. Maybe I can clean this up a little bit. I was trying to take a look at our patterns up here and see which identity that looks like. So if I compare that, if we had cosine, cosine, sine, sine, scrolling back down, the operation in between was a minus. So we'll have this version here. We have the cosine of A plus B. We'll just label that 87 is our A and 93 is our B. So this is the cosine of 87 plus 93. And we can go a couple steps further with this, because if we add 87 and 93, we get 180 degrees. And 180 degrees is a value off our unit circle, cosine being the x-coordinate, so this does simplify all the way down to be a -1. Okay, so essentially we just worked backwards here. We were given our expanded version, and we worked backwards to our identity, in this case the cosine of A plus B, and simplified down as we went. One more on this page, the sine of 195. So we're looking for two angles we can add or subtract, and again there are multiple combinations we can use. One that pops out to me right off the bat is 150 plus 45. Again, there's other options to use. I'm going to go with that one. I'll expand that out. Then the sine of 150 times the cosine of 45 plus the cosine of 150 times the sine of 45. Now it simply becomes pulling values off our unit circle, hoping from our work back in chapter 3 we're pretty well versed on that. Sine of 150 is going to be 1/2. Sine is the y-coordinate. Cosine of 45 is square root of 2 over 2. Cosine of 150 is negative square root of 3 over 2. And the sine of 45 is the square root of 2 over 2 again. So we have the square root of 2 over 4 plus negative square root of 6 over 4. Or we'll rewrite that as a single fraction as square root of 2 minus the square root of 6 all over 4. So there's our first look at our sum and difference formulas for our sine and cosine. Again, the patterns, I think after you write those down a handful of times, you might already have those ingrained, but you will very quickly here. Once again, I will point out that I will give these to you on the test, even though in my mind you probably shouldn't really need those. So we'll move on here. Along with our sum and difference formulas, a quick review of cofunctions. We had cofunctions back in chapter 2, I believe. Cofunctions are pairs are cosine and sine, so no sine and cosine, tangent and cotangent, and then secant and cosecant are all cofunctions, and that simply means their angles add to be 90. So the cosine of 30 is the same thing as the sine of 60. Angles are complementary, so their functions are equal to each other. The cotangent of 20 equals the tangent of 70 would be another example. Again, notice our angles are complementary, so our cofunction values are equal to each other. And secant of 10 would equal the cosecant of 80. Those just come some simple, straightforward versions of our cofunctions. We need to know our pairs. They should ring a bell from our work previously. Sine, cosine, tangent, cotangent, secant, cosecant. and the angles being complementary. Notice 90 minus theta and theta would be complementary angles. Okay, so our first one says just simply prove that cosine of 90 minus theta equals the sine of theta. So here is a difference of two angles. I'll say this is A and this is B. So I'll expand that out to be the cosine of 90 times the cosine of theta plus the sine of 90 times the sine of theta. You'll probably, hopefully notice anyway, that 90 is a value off our unit circle. Off our unit circle, cosine of 90 is the x-coordinate, that is 0. So 0 times cosine. The sine of 90 is the y-coordinate, that value on the unit circle is 1. We have 1 times the sine of theta. Obviously theta is not on our unit circle, that's a variable. And then looking here, 0 times cosine is 0, so that's going to be gone. And 1 times sine is sine, and it does equal the sine of theta. So a quick using of the difference formula to prove our cofunction values. Couple of quick questions here with cofunctions. Cotangent and tangent are cofunctions, which means their angles of x and 25 should add to be 90 degrees. They're complementary. So x plus 25 equals 90. We'll subtract 25 from both sides, and here x is going to equal 65 degrees. Okay, pretty straightforward, at least I hope so here to begin with. We'll start over again. Sine and cosine are also cofunctions, so x plus a negative 30 will equal 90. I'm going to go an additional step on this one. I'll change the plus a minus to be minus 30 equals 90. So I can simply add 30 to both sides. So in this case, x is equal to 120 degrees. And we'll go one more time here. Cosecant and secant are also cofunctions. Since they're set equal to each other, their angles are complementary. So 3 pi over 4 plus x. I'm going to leave it in radian measure. So I hope we all know that 90 degrees is the same thing as pi over 2 radians. So we're going to set equal to pi over 2. Rather than change this to degrees and use our degrees, we can just do our math here. Without making those conversions. If you want to change this to degrees and it's set equal to 90, that would be fine as well. But in this case, because our information was given in radians, we'd like our answer in radians as well. So to solve for x, I'm going to subtract 3 pi over 4 from both sides. And that means I need common denominators, so I have 2 pi over 4 minus 3 pi over 4, or x equals a negative pi over 4 for our x value. As a side note, if you did go ahead and put this as degree measures, you would get a negative 45 degrees, which again is the same thing as negative pi over 4. So hopefully we're pretty well versed in working with fractions and radians by now that we don't have to make that switch. Oh, we'll move on here. We use our identities to write functions in terms of a single function. So notice we have a variable here. We're just going to simplify this down as much as we can using values off of our unit circle. So the cosine of 180 minus x is the cosine of 180 times the cosine of x plus the sine of 180 times the sine of x. Again, that's just expanding out into our cosine of a minus b version here. Making our substitutions, the cosine of 180 is negative 1 off of our unit circle. Sine of 180 is 0. And much like we had just a few problems ago, 0 times anything is going to be 0. So this is going to simplify down to a single function of negative cosine of x. Single function, negative cosine of x. We'll start over here with number 9. Notice we have a sine and a difference. So I'll just kind of put an a and a b here again. Not that they're necessary. But we have the sine of 2 pi times the cosine of x minus the cosine of 2 pi times the sine of x. 2 pi as a radian measure goes all the way around, so we'd be back at the positive x-axis. Here, sine has a value of 0. And cosine has a value of 1. So we have 0 times cosine, which is 0, and negative 1 times sine, so this one simplifies to be a negative sine of x. One more time here, cosine of x plus 270. So again, we have our a and our b here with an addition. So the cosine of x times the cosine of 270 minus the sine of x times the sine of 270. Assuming we all can locate 270 on our unit circle, the cosine of 270 is going to be 0. The sine of 270 is going to be -1. 0 times cosine is going to be 0. Negative is going to make this a positive sine of x. So there's using our identities once again to simplify down as much as possible. Again, pointing out those identities are a pattern, so hopefully they're resonating pretty quickly here. A couple more problems to go here. This one says to find the cosine of a plus b and the sine of a plus b given the following information about a and b. Sine of a is 3/5, cosine of b is -12/13, and both angles a and b are in quadrant 2. So let's say we're going to start out with a cosine of a plus b. That would be the cosine of a times the cosine of b minus the sine of a times the sine of b. So I notice here for angle A, I need to know both the sine and the cosine. Right now I just know the sine. Somehow I'm going to have to be able to find the cosine. Same thing for angle B. I know the cosine, but I also need to know the sine of angle B. So what I would suggest we do is come over here, and I'm going to make a little T-chart for angles A and B. And I'm going to find X, Y, and R for each one of those. That way I can find my trig functions for each one. So notice the sine of angle A was given to us as 3/5. Well, sine is y over r, so I know y is 3 and r is 5. Sine again is y over r. That's a previous definition we should be pretty well versed in. Something else we might be well versed in is our 3, 4, 5 triangle. If we didn't know that, we could do x squared plus 3 squared equals 5 squared and solve for x this way. But I'd also point out the details here. Notice it says angle A is in quadrant 2. Well, I hope we all know that x is negative in quadrant 2. When I solved down here, I would have got x equals plus or minus 4. So in this case, it was a -4. Which would bring us to angle B. Cosine is x over r. So I have a -12 and a 13 here. We all should know the 12 has to be negative because in our coordinate plane or in terms of our trig function values, r is always positive. So it can't be 12 over -13. It's got to be -12/13. And same idea here, -12 squared plus y squared equals 13 squared. Or if we know our triangles, it's a 5, 12, 13 triangle. We're in quadrant 2 with angle B as well. Y is positive in quadrant 2. So now we have x, y, and r solved for both angles A and B. We can now make our simple substitutions. So back over here, cosine of A is -4/5. The cosine of angle B is -12/13. The sine of angle A is 3/5 y over r, and the sine of angle B is 5/13 or y over r as well. Okay, so multiplying here, I get 48/65 minus 15/65 or 33/65. So there's our cosine of A plus B. Having found x, y, and r should make finding the sine of A plus B go very quickly. So sine A cosine B plus cosine A sine B. So there's our identity formula. We found x, y, and r, so we can find sine and cosine pretty easy. Sine of angle A is 3/5. Sine is y over r. Cosine of angle B, cosine is x over r, so -12/13. Cosine of angle A, x over r, -4/5. And the sine of angle B, y over r, 5/13. -36/65 plus -20/65, we get -56. 65ths for our sine of a plus b. Okay, so finding x, y, and r made our substitutions over here hopefully fairly straightforward and simple using our sum and difference identities or formulas. One last problem to end our day. Verify the following identity is true, so we can't end these without doing some identities. Unfortunately, we did not have an identity for the sum for secant today. We have two angles, actually difference, but two angles being subtracted here. Good news is, however, that we have an identity for cosine, and cosine is reciprocal of secant, so I'm going to rewrite this as 1 over the cosine of 3 pi over 2 minus x. So now we have our difference formula for cosine, so I have 1 over, and we'll expand this out, the cosine of 3 pi over 2 times the cosine of x plus the sine of 3 pi over 2 times the sine of x. So this should look familiar to some of the work that we did up above in our previous couple of problems. Off of our unit circle, the cosine of 3 pi over 2 is 0 times cosine. The sine of 3 pi over 2 is negative 1 times sine. So now we still have 1 in our numerator. 0 times cosine is going to be gone. Negative 1 times sine is negative sine. And I hope we all agree that would be a negative cosecant as our identity. Okay, so there's our look at the sum and differences formulas for sine and cosine. Hopefully those are getting well ingrained already. After the assignment, they should be.